Hello and welcome to another screencast on biomechanics, and this time we're going to look into projectile motion for the first time. This is one of 4 screencasts on projectile motion, so please make sure you go through them in the correct order. So this screencast will start by defining projectile motion, and that's a movement of a body, remember that's an object or a person, through the air following a curved flight path under the force of gravity. A projectile itself is a body that is launched into the air, that it loses contact with the ground surface and therefore it travels. So that would be a good definition of what a projectile is. And often when we think about projectiles, we think about shuttlecocks, tennis balls, footballs, a rugby ball, a hockey ball, something that can be hit or struck or launched would be a good idea of what a projectile is. Now, how far a projectile travels is dependent on projectile release, and there are 3 factors that affect projectile release, and these are the speed of release, the angle of release, and the height of release. So depending on those 3 factors will depend on how far your projectile, in this case a shuttlecock or a shot put, will actually travel. There is a 4th factor that affects projectile release, which you will meet in later screencasts, and that factor is aerodynamic factors such as the Bernoulli principle or the Magnus effect. But again, you will meet that in later screencasts and not in this one. So let's look at these factors and how they affect how far something travels. Logically, the speed of release relates to Newton's second law of acceleration in the sense that the more force we put into an object, the faster it will travel. And so therefore, the greater the force we apply to the projectile, the greater the change in momentum and the faster it will accelerate. So if I push more force into my shot put, for example, logically, the further the projectile will fly or travel, therefore giving me greater distance. The second factor is the angle of release, which is a little bit more complex. So think about javelin throwers when you think about the angle of release, because that's the easiest thing to discuss in terms of a projectile example for this. And when we throw a javelin or when we throw any projectile, it's affected by the angle that it's released at. And we have different angles that we could try. So we've got 90 degrees, 45 degrees, greater than 45 degrees, less than 45 degrees. So the release angle usually comes into one of those brackets. How does that affect the projectile? Well, you can take a look at this chart. If we threw the javelin at a 90-degree angle, so straight up ahead of us, logically looking at the diagram, it would go up and it would come straight back down in front of us, and therefore the distance it would travel would probably be something like 0. It would just go up and down. However, if we throw the javelin at 45 degrees, so that is what we call the optimal angle of release, it should travel the furthest. So it's got a greater range in terms of distance it can actually travel and fly. If we throw a projectile less than 45 degrees, then as you can see on the 30-degree picture, it will travel in the air, but it won't gain great distance. It will come a shallow angle and therefore not travel very far. And the same can be said for greater than 45 degrees. Greater than 45 degrees, so if you look at the 60 degrees and even the 75 degrees, the projectile will travel upwards too quickly and then it will drop, not giving us a lot of distance. Of course, the angle of release is also affected by the other 2 factors, speed of release and height of release. And so those 3 factors often work together. But if we were just purely talking about angles, this is technically what should happen to a projectile. The third and final factor is height of release. Now, as we've just mentioned, 45 degrees is the optimal angle of release, but it's only optimal if the release height and the landing height are equal. So going back to my javelin, you're holding the javelin slightly higher than where it will land, and so therefore 45 degrees potentially is not the correct angle to throw a javelin, because the release height is slightly higher than where it's going to land. So there are rules with release heights and landing heights in terms of the height release. Therefore, if the release height, so the height of which you release the projectile to throw it, is above the landing height, the optimal release is therefore less than 45 degrees. So technically that would apply to our javelin thrower, because their hand and their arm and the actual javelin is above their head, but actually the javelin's going to land on the floor. The release height is technically higher than the landing height. However, if the release height is below the landing height, the optimal release becomes more than 45 degrees. So once you've got these two statements down, I'll give you some examples to show what I mean. Here's a good example of the release height is lower than where we want the projectile to land. So think about basketball. You're shooting a ball from a low position into a higher position, which is the net, and so therefore that release height angle has to change. Another good example of where the release height is lower than where you want to land it is in a golf bunker shot. So in a bunker you are deliberately below where you want that ball to land, and therefore you've got to strike the ball lower to make it fly at the optimal angle to get to the landing height. So the release height is lower than the landing height. Now you may be thinking, well, what other situation is there where actually the release height is higher than the landing height? Well, for this you need to think about, other than javelin, you need to think about sports where you've got to hit projectiles with great force. So tennis is a good example of that. The ball is thrown high in a tennis serve, and the point of where you make contact with it is the release height. So I'm hitting my serve from a very high position, but the landing height obviously is much lower because I'm aiming to hit the service box on the floor. So that's a good example of where the release height will be higher than the landing height. So hopefully that covers a few examples as to how those can be affected by height of release. Finally, in this screencast, we're going to talk about flight path diagrams. And we're going to talk about projectiles in flight. Once you release a projectile, it will follow a set flight path determined often by the size of the forces that act upon that projectile. And you're going to meet these forces as we go forward with describing projectiles both in lessons and on these screencasts. If the flight path is totally unaffected by air resistance, and therefore weight is the dominant force, it mirrors a shape in mathematics we call a parabola. When we throw a projectile, of course, the projectile, because it's thrown at speed, will always be affected by air resistance in some way, but it will also be affected by the weight of the object you are throwing. And so, as we just mentioned there, the classic shape of a flight path diagram is something we call parabola, which you can now see on the screen. That is a parabola shape. Now in the exam you are required to draw flight path diagrams for different projectiles. So you've got to think about two things. How heavy is the object you are throwing, or that is being hit, and how much air resistance is going to be put on that object as it travels with speed or over time. And therefore the flight path diagrams only come in two formats, and these are parabolic flight paths and non-parabolic flight paths. So we'll start to describe a parabolic flight path. You need to be able to define this, and you need to be able to draw this flight path diagram. So the drawing that comes up on the screen, please make sure you copy it into your notes. A parabolic flight path occurs if the weight of the projectile, so that if it was a shot put, for example, or another object, if weight is the dominant force, so it's a very heavy object, and the air resistance is less than the weight of the object, so the air resistance is small, then we get a parabolic flight path. And that parabolic flight path would look like that. So if I threw a shot put, technically, heavy object, it's going to hit some air resistance as I throw it forward, but the weight of that object is far greater than the air resistance that it meets. And so therefore, mathematically, that will create what we call a parabolic flight path. So you'll need to draw this diagram. That is a parabolic flight path. A non-parabolic flight path is the exact opposite. This time, if air resistance is the dominant force, so there's a high amount of air resistance on the object that you throw, and the object isn't that heavy, say compare it to a shot put, it might be a little bit lighter, then we get a non-parabolic flight path. Now basically, a non-parabolic flight path is any shape of a flight path that doesn't look like the one I've already shown you, which is the parabola. So it can look like a variety of shapes. It doesn't look like the parabola. So anything that doesn't look like the parabola is technically a non-parabolic flight path. So a good example of this is something like a shuttlecock. A shuttlecock flight path might look something like this. Because it's quite a light object, a shuttlecock, and the heavy tip of the shuttlecock is its weight, it will fly up very quickly, but then it will drop in a strange way. It won't drop like a shot put will drop. And so therefore, the flight path may look something like this that you see on the screen, and that's worth drawing. Other non-parabolic flight paths might be things like a javelin, might be things like a discus. These will all be non-parabolic flight paths because they don't land or are thrown in a flight path shape that is that parabola shape. Okay, thanks for watching this screencast, and again, if you need any more support on biomechanics or anything else with OCR A-level PE, please head to the ispeakPE channel on YouTube.